Good morning. Jai Hind, all the students. So today we are going to start the topic that is bipolar junction transistor. So here in today's topic, we are going to discuss about the construction and working of the bipolar junction transistor. Also the various types of the BJT. So what is transistor? Transistor means the transfer of the signal from the low resistance to the high resistance. What we mean by the low resistance to the high resistance, as we know that your transistor is a three-terminal device. And what are those three terminals? That is emitter, base and collector. So emitter base junction is forward bias, and because of that emitter base junction is forward bias, due to that reason it offers the low resistance path, whereas collector base junction is reverse bias, and because of that it provides the high resistance path, and that's why the signal flows from the low resistance to the high resistance. So the transistor basically consists of the two types. It is a three-layer device, and with it, or you can say the transistor is a three-layer semiconductor device, which is consisting of two N-type of semiconductor material and one P-type of semiconductor material. Means if a P-type of semiconductor material gets sandwiched between the two layers of the N-type of material, then we call it as NPN transistor. And if we say that the N-type of semiconductor material gets sandwiched between the two P-type of semiconductor material, then we'll get the transistor, that is the PNP type of the transistor. So NPN transistor consisting of three semiconductor region: emitter region, base region and the collector region. Similarly, PNP transistor or PNP BJT also consisting of the three region: emitter region. Here the emitter region will be P-type, base region will be N-type and the collector region will be P-type. Coming to the transistor construction part. So the transistor consisting of, as we said, that the transistor consisting of the three layers, and in the first figure we can see that the PNP transistor, it is having the three layers, and the total thickness of the transistor to the base thickness is 150:1. So the ratio is 150. The total thickness of the transistor is 150 to the base thickness is 1. Also, the doping level of the total doping to the base doping is 10:1. So we can say that emitter has the highest doping and the collector is slightly lesser doped than the emitter terminal, and base is the most lightly doped layer. So what does it mean? If we are increasing the doping, that means we are increasing the conductivity, and lesser doping means the high resistivity. So here we can see that there are transistors having the two PN junctions, that is the emitter base junction and the collector base junction. Also, here you can see the symbolic representation of the transistor. Here in the PNP transistor, the emitter terminal, the direction, the arrows represents the direction of the current flowing in the circuit. In PNP type of the transistor, the current is moving inward inside the transistor, whereas, and this depends upon that how the current is flowing in the circuit, whereas in NPN type of the transistor the current is outward, and we know that the emitter current is the total current, and which is consisting of the two components, that is the collector base current and the collector current. So the total current, if the emitter current is outward, then rest of the two current, that is the base current and the collector current, they are inward, and vice versa in case of the PNP type of the transistor. So emitter, the portion of the one side of the transistor, emitter is you can understand the word emitter, which emits the charge carrier, means it is the portion of that transistor that supplies the charge carrier, that is either the electrons or holes. Electron in case of NPN transistor, holes in case of the PNP transistor. So emitter is the most heavily doped, as I discussed earlier also, that emitter is the most heavily doped region. Emitter of the PNP transistor supplies the holes, charges to its junction, and in case of the similarly, emitter of the NPN transistor supplies the free electrons to its junction with the base. Collector means the terminal which collects the charge carrier, and it is opposite to the emitter side, and it collects the majority charge carriers. The doping level of the collector is heavily doped but slightly less than the emitter, and whereas the base is the most lightly doped material. So base is the middle portion and which forms the two PN junction between the emitter and collector, and it is called as the base. And base of the transistor is very thin as compared to the emitter, and it is the most lightly, and because of that it provides you the higher resistance to the flow of the charge carrier. So there are the two junctions present in the transistor. Why we call it as bipolar device? It is a bipolar device because the current conduction takes place by the two types of charge carriers, that is the majority charge carrier as well as the minority charge carrier, that we'll understand in the next few slides, that what exactly we mean by that. So there are the two junctions in the bipolar junction transistor, and each junction can be forward bias or reverse bias independently. So there are the three mode of operations. One is the forward bias, active mode, and the cutoff region. There are the three region of operation, I would say. One is the active region, second is the cutoff region, and third is the saturation region. So depending upon that how we are biasing the emitter base junction and the collector base junction, we decide that in which particular region it is your transistor is working. So if we are reverse biasing the emitter base junction and also we are reverse biasing the collector base junction, then transistor goes into the cutoff region, and that means it will be in the off state. Now if we are forward biasing the emitter base junction and reverse biasing the collector base junction, then transistor operate in the active region. In the active region, transistor act as an amplifier. The third one is the saturation region. In case of saturation region, emitter base junction gets forward biased and also the collector base junction forward bias. So it will in the on state. So depending upon the biasing, we can decide the application of the transistor. So if your transistor is operating in the active region, then it acts as an amplifier. And if we are operating our device between the cutoff and the saturation region on and off, then it acts as a switch. So the forward active region is as discussed earlier, that emitter base junction forward bias, collector base junction reverse bias, and here the transistor can be used as an amplifier and in analog circuits. Cutoff region, when both the regions are reverse bias, then it is called as in the cutoff mode, and in this situation there is only zero current and the transistor behaves as an open switch or in an off state. Saturation, in case of saturation region, both the junctions are, that is both the junctions means the emitter base junction and collector base junction, both are reverse bias, both are forward bias, and large collector current flows with the small voltage across. So here we can say that in this situation, the large collector current flows with the small voltage across the collector base junction, and here transistor behaves as a closed switch. So now coming to the working of the transistor. So for operating our transistor in a proper region of operation, we need to do the biasing. So the need of the biasing is to establish the Q point in the proper region of operation for the faithful amplification. So here we can see in the first figure, we can see that the emitter base junction has been forward biased. Here the example of the NPN transistor has been taken, and how do we bias the transistor in the active mode or in the active region? We will forward bias emitter base junction. So keeping the collector base junction open circuit means there is no biasing has been done right now, and this situation is similar to the ordinary PN junction diode in the forward bias state. So here we can see that the positive terminal of the battery VEE is pushing that means whenever your PN junction diode gets forward bias, what happened? The depletion layer gets reduced, and at the same time it pushes the majority charge carrier towards the junction. So the charge carrier will diffuse across the junction. Here we can see that because your base terminal is very thin and also it is lightly doped, that means it will provide the high resistance path. So very few amount of the charge carrier will contribute for the base current, and remaining charge carrier will diffuse across the junction. Now coming to the next second figure. In the second figure we can see that your emitter base junction has been open circuited, means no biasing has been applied, but your collector base terminal has been reverse biased because collector terminal is P type. So that is why in order to make it reverse biased, we have connected the negative terminal of the VCC to the collector and positive terminal to the base. This makes the collector base junction reverse bias. So here you can see that because of the reverse biasing, this situation again similar to the reverse biasing your emitter, your PN junction diode, reverse biasing the PN junction diode. What does it mean? That means first thing that the depletion width gets wider. Also, although you are reverse biasing the collector terminal, but because of the presence of the minority charge carrier in the collector region, they get forward bias and some amount of the current. So although majority charge carriers gets reverse biased by the reverse biasing of the collector base terminal, but it will give the forward bias to the minority charge carrier. That means the minority charge carrier will still be flowing in the circuit. This means that the current is flowing due to the collector base reverse biasing. The current which is flowing in the circuit, that is due to the minority charge carrier. So this is how we can say that collectively, if we'll see in the circuit, then when you are biasing both the terminals together, that is emitter base junction forward bias and collector base junction reverse bias, here the total current which is flowing through the circuit is due to the majority charge carrier as well as the minority charge carrier, and that's why it is called as the your bipolar device, because current conduction takes place by the two types of charge carrier, that is majority as well as whole. So if your transistor is PNP type of transistor, then the majority charge carrier will be holes and minority charge carrier will be electrons. And in case of NPN transistor, electrons will be the majority charge carrier and holes will be the minority charge carrier. If somebody asks you that out of NPN transistor or PNP transistor, which transistor has to be used, preferably used, then what will be the answer? The answer is that your transistor should be NPN type. Why? Because it has high efficiency. Why? Because the mobility of the electrons is greater than the holes. So, the total current which is flowing in the circuit is the emitter current, which is sum of the collector current and the base current. So collector, because the thickness of the collector current is very base terminal or the base layer is very less. Also, the doping is very less. So the base current is of very small amount of the order of microampere, and emitter current and the collector current, they are of the order of milliampere. And the collector current is basically consisting of the two components, that is the majority charge carrier as well as the minority charge carrier. So ICO is the minority charge carrier current, and it is also called as the leakage current or the reverse saturation current. So now coming to the basic configurations of the bipolar junction transistor. So basically, BJT is a 3-terminal device. We know that it has having the 3-terminal emitter, base and collector, but any network is a 2-port network, means 2 terminals at the input side and 2 terminals at the output side. So how do we get out of these 3-terminal device, how do we get that 2 ports, 4-terminal 2 ports? So the answer is, if we make one terminal common to the input as well as output, we can get the device, that is the we can get the 2-port network. So here comes the 3 types of configuration into the picture. One is the common base configuration, where the base terminal will be common in the input as well as in the output side. In case of common emitter terminal will be common at the input as well as output side, and similarly in case of common collector terminal is common in the input as well as at the output side. So why we require 3 types of configuration? Why not one configuration is sufficient enough? So the answer is, all 3 are having their different characteristics as well as their application. So in one point, if I'll explain right now, I can say that common base configuration or the common and the common emitter configuration, they are basically used as for the voltage amplification. So they are used in the voltage amplifier, whereas common collector, which is also termed as the emitter follower, its voltage gain is nearly unity. So then the question arises that if it is giving the voltage gain unity, then why it is called as an amplifier? Because it is not amplifying any voltage. Then the answer is, it is a current amplifier. It has the high current gain. Also, the voltage amplifier, common base and common emitter, they both are having the different applications. Means the common base is used for the high frequency signal amplification, and for low frequency signal amplifiers, common emitter is used. So common emitter is the most widely used amplifier in the practical applications. Common collector is as I said, that common collector is an current amplifier. Apart from that, it is also having one application, because the common collector is having the low, it is having the high input impedance and low output impedance, and it is having the voltage gain unity. So it is used for the it is used as an impedance matching device in the multi-stage voltage amplifiers, because it gives the it does the impedance matching between the 2 stages of the amplifier without disturbing the actual gain of the amplifier. So basically, the application of the common emitter common collector amplifier or the amplifier or the emitter follower is, it is used for as an impedance matching device in the multi-stage amplifier to reduce the loading effect. So this is the application of these 3 transistors as a common base amplifier, and the common emitter amplifier. They both are actually having the low input impedance and high output impedance. So now coming to the input-output characteristics of the common base configuration. So here we can see that in case of the common base configuration, the base terminal is common in the input side as well as at the output side. Again, the emitter base terminal is forward bias, and because this is an PNP type of transistor, so we can see that P type of material to be connected to the positive terminal of the battery, and collector terminal should be reverse bias, and collector is again a P type of material, so it should be connected to the negative terminal of the battery to make it reverse bias. So now the input characteristics of the transistor is between the input voltage and the input current. So VEE and VCC, these are the biasing voltages, but the input voltage is the voltage which is appearing between the emitter to base terminal. So VBE is the input voltage, input current is IE, and keeping your output voltage constant, then we get the input characteristics of the common base configuration. So in that particular case, we can see this situation is similar to the PN junction diode in the forward bias state. So here we can see that initially your current is almost zero, because here the example has been considered that the diode is a silicon type of diode, and because of that the current is almost zero, because that amount of the voltage 0.7 is the barrier potential of the PN junction diode. So that amount of the voltage has been consumed to overcome the barrier potential, and after that your current will start increasing. Here it is very important to see that although we are changing the collector to base, that is the reverse voltage, from 1 volt to 10 volt to 20 volt, but the curve is almost same. This is the 3D picture. So that is why you can see 3 diagrams, but actually they are almost overlapping each other. What is the reason? The reason is that the collector base terminal is reverse bias, and because of that it will offer only the current that is due to the minority charge carrier, and minority charge carrier current is very small amount. That is the leakage current, and that is why it does not have any effect on the input characteristic. That is, emitter current is almost same by 3, although you are changing the collector to base voltage. Now coming to the output characteristics of the common base configuration. Output characteristic means the characteristic curve between the output voltage and the output current, keeping your input current constant. And because here you can see with the from this characteristic curve, we can see that although you are increasing the VCB from 0 to 20 volt almost, but the current is almost getting constant. And this is the reason, because your output current is independent of the output voltage. It depends upon the input current. Whatever input current we are going to fix, the output current is almost going to be, it is almost equal to the emitter current, and that is why we call it as the current control device. Because in case of the bipolar junction transistor, output current is controlled by the input current, not the output voltage. So here you can see that if we are keeping our emitter current 0, that means we are not biasing the emitter base terminal, and then in that case the whatever current is flowing in the circuit, that is only due to the minority charge carrier, and that's why the current is almost 0. It is very small amount of the current, that is of the order of picoampere or something like that. So if we set the emitter current 1 milliampere by forward biasing the emitter base terminal, then the collector current will be almost equal to the emitter current, means slightly less than the emitter current. Kitna kam? How much less? It is the lesser amount, that is the base current. Base current means the collector current will be equal to IE minus of IB. So whatever current we are going to get at the output terminal, that is the equal to the emitter current or the input current. So this shows the graph demonstrate the output current to the output voltage and at various levels of the input current, that is the emitter current. So these are the 3 operating region. Here you can see the saturation region, cutoff region and the active region. So whenever we would like to operate our device as an amplifier, we must operate our transistor in the active region, and if you would like to operate our device as an switch, then it must be operating between the cutoff and saturation region. So with this note, I complete this lecture for today, and we'll continue for the common emitter and common collector next coming video. Thank you. Jai Hind.